So in the last video I showed you how to do this problem with the z-tables, and it's a little complicated because the numbers in the z-table only give you the area to the left, and so you have to figure out, what I did was figured out the area to the left and then the area to the right of 0.81 and use symmetry to do that because the table only gives you the area below. If you want to do the area to the right or above one in the picture, you can use symmetry and do the area below the negative of that value is what I did. But anyway, there's a much simpler way to do that if you want to do it with a Texas Instruments calculator here. So let me pull the emulator in, clear out my algebra there. So these things are under distributions. You have this button for variables, VARS. If I do second and that button, I get some different things that we're going to use throughout the semester. And with the normal distribution, we're going to use normal CDF and inverse norm quite a bit. We don't use the normal PDF, we use the cumulative density function is what this stands for. So we're going to use number 2 there. And so you can either go down with the arrow and hit enter or just hit the number 2. So I do, again, second and the variable button to get to this menu and then select number 2. And the older calculators don't give you this menu. You may have a calculator that doesn't give you this menu. In that case, what you would do, it'll pop up on the screen, it'll say normal CDF, and then you'll have parentheses, and you put the lower bound, comma, and you use the 7, above the 7 you have the comma, and then the upper bound, and then comma, and then mu, comma, sigma. So you'll put these 4 numbers in as what we call arguments, the values inside parentheses. So on your screen it'll say normal CDF, and then this is the value we're going to use later for negative infinity. Your calculator, you can't use infinity, so we use 1E99. That E is the thing that's above the comma. If you hit second the comma, that's scientific notation. So just while I see that there, I'll go ahead and tell you negative 1E99 is negative 1 and 99 zeros. It's a huge negative number, which is our substitute for negative infinity. If we want to do positive infinity, we could do 1E99. But on the calculator, you have to give it the 2 values, so it's perfect for this problem. So my lower limit, if I get the menu, I just type it in here. My lower limit is going to be negative 1.25. And then my upper limit on this problem is 0.81. So I want to find the area between those 2 values, below the graph and above the x-axis, but between those 2 values. And then I can give it mu and sigma, and for the standard normal, that's the default here. We have 0 and 1. If you have a different distribution, you don't have to go through z-scores. You can use the 0 and 1 to do it. So if I do paste, it'll actually show you what it looks like if you don't get the menu. It'll just pop up on your screen with normal CDF, and you have to type these things in the right order. It's always, if you want to find the area between A and B, it's always A and then comma B, your lower limit, comma upper limit, comma mu, comma sigma. Hit enter, and it'll instantly give you a value with a lot of accuracy here. Okay, using the tables, I got 0.6854. Here we've got 0.6854 if we round, but we have more decimal places with our calculator. So we can very quickly get the area between any 2 values under any normal distribution with any mean and standard deviation that we want using normal CDF on our calculator. But let me show you one example where I use z-scores directly. Okay, so yeah, if you want to find the area represented under the graph there for any particular normal distribution, you don't necessarily have to go through z-scores if you have the right technology, but z-scores are still useful on their own. Okay. I have one example that I usually do in class with baseball batting averages. If you compare players from different decades, there's different standard deviations and averages for the entire league during the different decades, so they're coming from different playing periods, different distributions. We can standardize them, look at the z-scores, and compare them. I'm going to do that here with test scores. So we get the SAT and the ACT. These numbers change over time. Originally, the SAT was written to have a mean of 500 and a standard deviation of 100, so we're going to go with that. Let's assume the SAT has a mean score of 500 with a standard deviation of 100, while the ACT test has a mean score of 18. The ACT only goes up to 36, so the mean of 18, standard deviation of 6. So if we want to compare a student that got a 680 SAT to a 25 ACT, which is something colleges have to do if students take different tests, you can't compare those directly because they're on completely different scales, but what I can do is, we call it standardize them. We do the z-scores. Okay? So the SAT is normal, or at least approximately normal, with a mean of 500, standard deviation of 100. Your z-score, if you look back, the formula is your x value minus mu divided by sigma. So this would be your 680 minus that mean of 500 divided by the standard deviation of 100. So that's going to give you 180 divided by 100, or 1.8. So that means, I think, yeah, I put this in, I typed it in. What does that tell you? That tells you how many standard deviations that score is above the mean, since it's positive. A 1.8, that student scored 1.8, or a little less than 2 standard deviations above the mean for the national average of 500. We can do the same thing with the ACT, which is normal with a mean of 18, standard deviation of 6. So we take a score of 25 and subtract the mean and divide by the standard deviation. We wind up with 7/6, or 1.17, which means that the 18 on, or the 25, I'm sorry, the 18 is the average. The 25 on the ACT is about 1.17 standard deviations above the mean. So that allows us to compare them. The 680 SAT is more standard deviations above the mean than the ACT. So compared to the rest of the people taking the particular test, the 680 SAT is more impressive. Okay? They're more standard deviations above the mean. They have a higher z-score. So the SAT score is, I put in quotes there, better. It's not a perfect comparison, but it's one way to do it. Okay? If you have different means and different standard deviations, you can standardize and compare how many standard deviations you are above or below the mean.